All right, here we go. We're going to go through 2.4. It's not horribly long, but as far as pages goes, but it takes a little bit of time. And we're going to look at complex zeros of a polynomial. So now we're getting outside of requiring that we are only looking at the real solutions, and we're going to look at the complex solutions. Now, a complex number is of the form a, so some real number a plus some real number b times I. So a plus bi like that. For example, you could have -2 plus 3i, or even just something like 4i, or something like that. They're complex numbers. And then what happens is you have our real plane along here. You have the imaginary plane going vertical, kind of like the y-axis. And so we have like 0, 1, 2, 3, like that. And then this also can go down. And then like -1, -2, -3, like that. And then up here this way you have I, 2i, 3i, like that. And so, for example, if we wanted to do -2 plus 3i, we'd go -2 here, right? We're going to go -2 over to here, and then we're going to go up to 3i. 1, 2, 3i right there. So that's right where it would land us. And so we would have something like that, and then we would say, okay, that we point straight from the origin out to right there, and that's where that negative, that complex number lies over there. A couple of other interesting things, of course. What is I? I is defined as the square root of -1, which also then implies that I squared equals 1. So this is how we can take care of the square root of a negative number. Another very interesting thing is that I'll show you this one. I is equal to 1 or -1 over I, like that. And so we can show this by multiplying it by I over I, which is just 1. And that gives us I squared over I, but I squared is -1, and so I kind of wrote that a little far away. Since I squared is 1, we just get that, -1 over I. So it equals the negative of its own reciprocal. Kind of interesting little thing about that. All right, so let's go ahead and try this. If we look at this first example, we can just solve this by using the property of square roots. So x squared plus 1 equals 0. That means x squared equals -1, which means x equals plus or minus the square root of -1. But as we just set up here, square root of -1 is just I. So x equals plus or minus I. All right? So we'd have x equals I and x equals -I. And if we wanted to write this like in the complex thing, then this one would be like 0 plus I, and this would be 0 minus I. But we don't usually write the 0 if there's not a real component to it. All right, let's try the next one. Here we have x squared plus 10x plus 25. That's pretty easy to factor because 5 times 5 is 25, and 5 plus 5 is 10. So this will be x plus 5 times x plus 5 equals -4. And so this is x plus 5 squared equals -4, which means we can take the square root. So x plus 5 equals plus or minus the square root of -4. And square root of -4 is actually just square root of 4 times the square root of -1, like that. And that square root of -1 is I. So this is just going to be square root of 4 times I. Right? That just is I. And so square root of 4 is just 2. Square root of -1 is I. And then we can subtract a 5 from both sides and get x equals -5 plus or minus 2i. So that gives us our answers, our two answers of x equals -5 plus 2i, and x equals -5 minus 2i. Okay, so that's how we got that. This next one says, find all the solutions of the following equation. This is x minus 4 times x minus 2i times x plus 2i equals 0. So if any one of those are 0, so if x minus 4 equals 0, if x minus 2i equals 0, or if x plus 2i equals 0, any one of those things is going to solve this for us. The x minus 4 tells us that x equals 4 is a solution. The x minus 2i tells us that x equals 2i is a solution. And the x plus 2i tells us that x equals negative 2i is a solution. So we have our three solutions right there. Those are all the solutions to that one. So this brings us to something you may have noticed, which is the conjugate pairs theorem. All right, which is essentially what we have is a complex conjugate, where any complex number we have, like z equals a plus bi, then its complex conjugate right here, a minus bi, which is just take all the values that have I in them and make them negative, is also going to be a 0. So if a plus bi is a 0, then a minus bi is a 0. So you can see this up here. I was a 0, and then so was negative I. Over here, negative 5 plus 2i and negative 5 minus 2i were both zeros. Down here, 2i was a 0 and negative 2i was a 0. So those are the complex conjugate pairs right there. All right, so be careful with that one. This is an important idea, that if you get one complex answer, then its complex conjugate is also going to be an answer. So let's take a look here. It says find the remaining zeros of the polynomial described. They tell us it's degree 5, but then they only give us 4 zeros. Okay, I'm not 4 zeros, I'm sorry, 3 zeros. This is 1. They give us that 1. They give us 3 zeros, even though there are 5 zeros. So what are the remaining zeros? Well, negative 5 is a pure real number, so we can't do anything with that. But negative 1 minus I, we can take the complex conjugate of that. That's negative 1 plus I. And then we have 10i, which we can take and do negative 10i. And so that's the remaining 2 zeros right there. This one and this one. Just taking the complex conjugate the complex conjugate of the imaginary ones. All right, next, the number of zeros theorem. This tells us that any polynomial of degree n has exactly n zeros, counting multiplicity. All right, so sometimes the numbers repeat, but you still count it. So if a number has a multiplicity of 3, it counts as 3 of the zeros. And then here, this is the rest of the part of here, it's that some zeros may be complex. So up until this point, we were finding zeros, but we didn't always find however many there were, because some of them might have been, they were not real answers. Well, now we're going to include the real answers, and we're going to include the multiplicity. And so we know exactly how many zeros we should get just by looking at the degree of the polynomial. All right, so that's going to be very useful to us. Like up here, we can see it's degree 5, and we have 1, 2, 3, 4, 5 zeros. And up here, this was a degree 3, right here, degree 3 x, 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 and we ended up with 1, 2, 3 zeros. If we look at this one, it's degree 2, and we ended up with 1, 2 zeros. This was degree 2, and we got 1, 2 zeros. Okay? So let's go on to the next page here. How do we factorize, or factorization of a polynomial? So how do we factor them? And any polynomial p of x of degree n is greater than or equal to 1 can be written in the form p of x equals a times x minus c1 times x minus c2, keep going, all the way to x minus cn. However many, whatever the degree is of the polynomial n is how many of those terms you're going to end up having. And then this is where a is the leading coefficient, like that. And C1, C2, all the way up to Cn are the zeros of P of x. Okay, so let's try this out and see if we can take advantage of this right here. It says find an nth degree polynomial function with real coefficients satisfying the given conditions. Write the polynomial in both factored and expanded form. All right, so let's first look at this. They tell us n equals 4, so they're telling us degree is 4, and therefore there are 4 zeros. Okay, you can see here they list us 1, 2, 3 zeros, and then they tell us a point that this goes through. In other words, this tells us that the point 3, 160 is a solution. Okay, and we're going to use that. We're going to use this to find what the leading coefficient is, to find A. So if they tell us 3 of the zeros, but we know there has to be 4, we can simply take the one and only complex 0 and add on its complex conjugate, so just negative I. So now we have all 4 of them, which means we can come down here and write P of x equals, and then we can write this in our factored form, A, and then we can do x minus 1, that comes from that one, and then we can do x minus negative 1, so x plus 1, that comes from that one. We can do x minus I, coming from that one, and x plus I, just like that, coming from this last one. And there we go, we have that in our factored form. However, we're missing what A is, so let's try and find A. Find A. Well, actually, let's find A after we compress this a little bit. So this is all factored out. We're also supposed to find the expanded form, so let's go ahead and start doing that. So we'll bring the A along. X minus 1 times x plus 1. All right, we can start with that one. X times x, and just go term by term. X squared minus x plus x minus 1. And then we can do this one, x minus I times x plus I, and that'll be x times x squared minus xi plus xi minus I squared. We can simplify those down. This is a times x squared minus 1, because those two will cancel, and then these two will cancel, and so it'll be x squared minus 1 times x squared, and so I squared, remember, is negative 1, so this will be x squared plus 1, just like that. Then we can go ahead and multiply those two together, and you get a, and then you get x to the 4th, and you get a minus x squared and a plus x squared, and then you get a minus 1. So the minus x squared and the plus x squared, they cancel, and you get x squared minus 1. If you don't see that, then try actually, doing each term by term multiplication, and you'll see that that will all cancel out. Okay, now we're going to find A. So we're going to come up over here, and we're going to find A here. And to find A, we can plug in that point 3, 160. So finding A, we plug in 160 equals A times 3 to the 4th minus 1, just like that. So we're just plugging that in. 3 times 3 is 9. 3 times 3 is 9 again, and 9 times 9 is 81. So, because that's like 3 squared times 3 squared. So this is 81 minus 1, which is 80, and then A equals 2. Divide both sides by 80. A equals 2, and so finally we can write both the factored form and the expanded form. So in the expanded form, we can say P of x equals 2 times x to the 4th minus 1. And then for the factored form, we can say P of x equals 2 times x minus 1 times x plus 1 times x minus I times x plus I. Just like that. And there's our two answers for that. And again, if I went too fast or any of that doesn't make sense, just back up the video and try it again. So for this next one, let's go ahead and just try this one more. We have n equals 3, but they give us 2. So this means we have degree 3, and we should have 3 zeros, which means we have to add one more on. If 5i is a 0, then so is negative 5i. And then they're giving us the point -1, 156 as a solution there. So we can use that to get what a is. So let's write out our polynomial. P of x is a times x minus 2 times x minus 5i times x plus 5i. Okay? That one gives us that one, that one gives us that one, that one gives us that one. Okay? Now we can go ahead and start multiplying this all together. So right here, and this is a nice little trick. You may have noticed it kind of happened up here. X minus I times x plus I, whenever you multiply a complex number by its complex conjugate, you end up getting the complex numbers to cancel out. And you end up with a purely real number like that right there, which is just the x squared plus 1. And so if we look at this one here, we'll have the x minus 5i and the x plus 5i, and it'll turn out it's going to be x squared, right, plus 25. And if you do that whole thing out, you will see that that actually occurs. If you do the x times the x and the negative 5i times the x and all that kind of stuff, if you FOIL that whole thing out, you will get that. So give that a try, and you should see that it's going to work out to be that way. So it's just this squared plus this squared. And work out nicely for us every time. And so now we need to do this one last FOIL, this multiplication, and we end up with a times x squared is x cubed, x times 25 is 25x, so we're just going in here every term, then a minus 2x squared, and then a minus 50, just like that, and a minus 50, and at this point, there is our fully expanded form, and so we have the factored form and the fully expanded form. All we have to do is find a, and to do that, we'll take advantage of 156 equals a times, and then we'll have -1 to the third plus 25 times -1. I don't know if I gave myself enough room here. Hold on, let me move this over slightly. Okay, plus 25 times -1 minus 2 times -1 squared minus 50, just like that. And so then we just start expanding this all out. So this is 156 equals a times -1 times -1 is +1 times -1 again is -1, and then minus 25, and then minus 2 because -1 squared is a +1, and then minus 50. And so if we look at that, those are all negative numbers. We end up with -1, minus 25, that's -26, and then -27. And so 50 plus -27 is, or -28, I'm sorry, not -27. -28 is going to be -78 over 156. And so that gives us an a equals -2 here. Okay, and now we can simply plug that back into our expanded form and our factored form and get our two answers. So for the expanded form, we get p of x equals -2 times x cubed plus 25x minus 2x squared minus 50. And you could even multiply that -2 through if you wanted to. Like you could do -2x cubed minus 50x plus 4x squared plus 100, like that. You can do that and say, all right, there's the fully expanded one, and then we can have the factored version, which we get from up here, right, from right there, and that's going to be -2 times x minus 2 times x minus 5i times x plus 5i, okay? And that's our fully factored form. Okay, that's pretty much it for this chapter. If you have any questions about it, just let me know. Otherwise, go back, watch it a couple times, and make sure it makes sense to you. All right, thanks a lot. That's all.